Hello everyone, my name is Joe Scarr. Today we're going to take a look at a quote-unquote simple sphere packing method in TP using TP 6.6. I want to give a shout out to Fabian Buckris for posting that sample file in the Facebook TP group where he modifies the size of the particles using a p-search method like we discussed. And today we're going to take a look at something a little bit different. I've got a method here where particles can start overlapping, and what they do is they reposition and resize themselves based on, stuff. So let's go ahead and we'll get started. Let's reset this. Of course, we're using standard film conventions, so our starting frame is 1000. TP is going to start on 1001. Real time is off, so that TP calculates every frame. Let's go ahead and get a TP in here. Alright, so the beginning thing we need to do is create a first dynamic set called system, which is where we're going to store all of our stuff. This way we make it modular, it can easily be turned into a black box. Also, we're going to have a corresponding system group, and inside that group, we know we're going to have at least two groups. One of them we're going to call sources, or in this case we'll call it source surfaces. And this is going to be called packs. And packs are going to be what get packed into that space onto the source surfaces. Let's go to this. Just so I don't have to do a double S, let's call it sources. And this, and set it to text. Great. Alright, so we're going to need two rules. We're going to need to give birth, and then we're going to need to pack. So to do this, zoom way in, we're going to create a simple plane as our starting surface, because you should always start simple when developing a complex project. If you don't start simple, you are going to be doomed by complexity, or at least get extra challenges because of complexity. Keep it simple. Make sure it works and does what you think it does, and then go ahead and make it more complex. So one thing we need to do is bring this plane into TP. We're going to use layer to particle. Let's go ahead and put that on its own layer. Call this sources. TP, let's put it on its own layer. Call it TP. And make the active layer up there. Okay, so sources, I'm going to come in here. We're going to put them in the group sources. Instance shape on by default. Good job, Cebas. Sources. Alright, so sources are going to create some packs. So each source who comes out is going to be creating some packs. In this case, we're going to start with 2. Keep it nice and simple. No speed, no alignment difference. We're going to go ahead and birth on the surface of sources. And remember, if you are going to use more than one output from here, like position and alignment, that you cannot do this, because these, without a particle to control the sampling, each one of these samples is going to be from anywhere on the mesh. So to do this properly, particle in, and let's use particle data. That tab menu, it's great, but I'm still not used to it. Boom, particle data. Let's go ahead and set the position and set the alignment. Make sure that's set to face. Great. Okay, so let's see. Let's hide our sources layer. Do we get what we think we're getting? Let's make sure TP is set to start at 1001. That way we get a nice safe reset frame at 1000. Yay, alright, so we get our stuff. We get 2 particles, we get our red source grid. Alright, so now we need to, let's give these pack particles some properties at birth. We could build a whole system for you, but we've got one already under basic called at birth. And what we're going to need is some shape for those. So let's go ahead and we're going to create a new layer. Or actually, let's create the object first. We're going to create a tiny little geosphere whose radius is 0.5, so that its overall diameter is going to be 1, meaning its size in TP is also going to be 1, because TP uses the longest edge of the bounding box of a particle shape as its size. Always the longest. Okay, so let's pick this put that on its own layer. Particle shape. Shapes, sure. Okay. Okay. So now, just have some shape on there. It's really, really small. So let's go ahead and modify this. You can see each particle at birth gets a random number between 0 and 1. That gets fed into a value to lookup table, basically, or a fit if you're coming from Houdini. And what this does is it says, if the incoming value is 0, then use, this is on the x-axis, 0 is here, 1's over here on the right. Get that interpolation and find out, and then, so if the incoming value is 0, our y value is going to be 0, but our y output for 0 is actually going to be 0.1. As our random incoming number goes from 0 towards 1, it's going to be going up in y up to a value of 1 at the maximum. So this is just a nice way of creating kind of a random weighted value. So most of our particles are going to be here in the lower zone, some are going to be in the middle zone, and only a few are going to be really big. So let's modify this so that, let's turn off edit on the fly so that as we make changes they show up immediately. Okay. Now we want a little more randomness in between these particles, so let's go ahead and change this. Well, we could also modify the okay, this is a good example. Alright, so what we have here is two particles overlapping. I'm going to use Green Shot. If you don't have Green Shot for screen capture software, you might want to check it out. It's totally awesome. And we've got a big particle and a small particle. And what we want to do is we want to figure out where should the small particle go in order to not be overlapping. Of course, the overlap we can tell, because they're spheres, we can tell by their radius, or radii. The big particle radius and the small particle radius, we need to add those two together, and that's going to tell us that this position needs to move up here. Alright, so we're going to do that by setting up our pack rule. Pack rule says, hey, I want the packs to be searching for other packs. So each and every pack does a search. It's going to look for the group, which is his own group. So it's going to look for all of his siblings. We're going to set the radius to 50 just for this test. Based on your world size, you have to modify that. And what we want to do is we want to compare the sizes of these two. Now, in order to compare the size of a p-search found PIDs, we need to use the particle data helper, not the operator. And we're going to, not the age, but we're going to look at the size. Because we want to figure out, hey, which one's smaller, and we want to affect the smaller one. So we could use threshold, but I'm going to use a condition, which is an expression called less than. So this says, hey, if A is less than B, output 1, which is true, or output 0, which is false. So let's do that. So if my size is less than that size, then this pack is going to be modified. We don't want to modify the found PIDs just yet. We will in a little bit, but so what we want to do then is we want to figure out, okay, well, what is the minimum distance between the two? So to do that, we're going to look at their radius value, or half their size. So we're going to multiply size by 0.5. Let's call this half. Okay, so we take half of that size, half of the found particle size, the other found particle size. We're going to add those two together. This is going to be our minimum distance. So we're going to add that. We'll call this min dist. Okay. So we want to compare the minimum distance, where do they have to be versus where they currently are. So to do that, we're going to look at found distances. Now remember, each and every pack is doing a search. the pack might find multiple particles. For each particle it finds, it outputs, it can output all of this data per one that it finds. That's important to remember. So what we're going to do is we're going to look at the found distance and compare it against the min distance. And what we want to say is if the found distance is less than the minimum distance, then we need to modify the smaller particle. So let's do that. Let's say, hey, if the found distance, in this case, we're going to subtract the minimum distance. What's the difference between them? And remember, if the found distance is smaller than the min dist, this value is going to be negative coming out. So that negative value is going to affect how we create an offset vector. We'll get into that in a second. So if our distance is negative, use threshold, say, hey, is it inside 0 to negative 99999? Big negative number. So is it in negative territory? If it is, and if my size is less than the other one, then I want to do something. Okay, and what we're going to do eventually is we're going to modify the particle position. For that, we're going to use particle data. You'd like to use particle data because it allows you to pre-compute positions as well as set other parameters if you need to. The position operator is great as well, but we're just going to go ahead and use this for now. So what we're going to do then is we're going to say, okay, is negative, the difference between the two is negative, meaning they overlap. Then I want to create a new vector that goes basically in this direction, and I want the amount of that vector in that direction, the magnitude, I want that to be the difference in, okay, so this is our, remember, this is our minimum distance, and this is our actual found distance. So this left over here, that's the amount that we have to displace by to give us our new position, which will be out here somewhere. All right, getting a little messy there. But anyway, the point is, remember that, but we are calculating the difference between the minimum and the found, which is going to be a negative value. So in order to get a vector that offsets in the negative direction, we need to set up our detect that direction in a certain way. Now it's really easy in TP. You can always just wire these up, and we want to compare the position of the current pack with the position of the pack that I found. And that direction, if it doesn't offset in the right way, we can flip these inputs around to get the correct one, but you'll see. So we're going to use a math operator here to create that offset vector. You need a vector and a float. We're going to multiply the vector by the float. The direction is just a pure direction vector. It has no length, or it has a length of 1. And then our, what is it, our difference? Our difference here comes in this way. Getting a little bit cramped on space. Okay, and so this offset vector, we need to add the small one's current position with the offset vector to get a new position. And some people have been asking about vector math a little bit lately, so let's just go through this real quick. So here's my current position, here's this guy's position. Basically we're going to get a vector, currently we're set up, actually it points this way, but the difference is negative, so it's actually going to end up offsetting in a negative direction. But we want to take this current position and we want to add another vector to push us out to this position. So we're just going to duplicate that math node, take the another vector. We're going to connect the vector to our current pack who is searching. When you connect a vector to a particle, it grabs the position. We're going to take that offset vector, add that offset vector to my current position, use this as my new position. Now if we did this right, it'll go into the right place. Yay. If these are flipped around, then it's going to go closer. Okay, so obviously we don't want it going closer. Let's go ahead and flip this around. If you analyze the logic for, distance uses position 2 is the starting position, position 1 is the destination, but we've got a negative value coming out of here, so that actually makes that direction negative. It all works out. So as you work more and more with vectors, that just becomes kind of second nature. So we have this going over there. Now what we want to do is we want to get a little more complicated, where we say, hey, if I'm off the surface, if my particles are so big that one of them would be pushed off the edge, then I want to modify the size of the particle. So let's do this. Create you up here, create like that. All right. So we can see clearly this guy is off the edge. And what we're going to do then is we're going to look and say, hey, this is the offset vector, or the what I'm going to call the proposed position, the new proposed position for the particle. And I want to find out, well, where's the nearest point that's still on the surface? And if that nearest point that's on the surface is less than the minimum distance, if it's less than that, well, then I need to move that particle, that position on the surface, and I need to make that particle smaller. Okay, so how are we going to do that? What we do has to do with our particles, our packed particles, knowing about their parent surface, the sources. So that's really easy. We just create a reference, right? Once you just create a reference between the two, either of them can look up data about, oh, who's my parent or who's my child. So always remember with setref, come up with a naming scheme or a scheme that works well for you. I like to think of particle from as the parent, particle 2 as the child. All right, so in here, now what we're going to do is we're going to access that parent. We do that by saying, hey, give me the packed particle. And the packed particle, of course, is the to me in that relationship. And what this does is says, hey, get the reference particle where the incoming particle is the to, meaning I have the child. Now I want the particle who references the child. And what we want to do, in order to use the nearest point on geometry, we're going to use the geometry operation for that. This is under geomParticle, closest point by surface. But we need to convert this particle into an object. Now that's really easy now in TP. Thank you, Cebas, for adding a particle A and particle B input onto the object. This converts that particle into an object, and now we'll be able to access closest point by surface as well as that closest point distance. That closest point distance is going to tell us, we're going to compare that against the minimum distance in order to determine, hey, I need to change my size. So this is going to start to impact these conditions of how many true conditions have to happen for certain things to happen. We're either just going to move the position, or we're going to move the position and change the size. So what we're going to do is we're going to expose not the particle input here, but the position input. Something new that Cebas added based on user feedback, where we can now say, look at the object, but use a position instead of a particle, and using that position, figure out the closest point on the surface. Well, remember this addition over here, this is the offset plus our original position, so this is really what we're going to call a proposed position, or proposed post. So let's use that proposed position as the origination, which is, no, that's not the one that I wanted, nor is that. The proposed position is here, but the actual nearest is here. And what we're going to do is say, hey, what's the difference between those two? And if the difference is really small, then it must be valid. But if the difference is big, like this, then it's off the surface. So that's pretty easy. We'll just use a threshold to say, hey, what's that closest point distance? How far is that proposed distance from the actual nearest surface position? Okay. we'll say is near or is close enough. So is it inside? Is it between 0 and say 0.5? And if it is within that, then we can go ahead and use that first condition. And I know this is a little bit confusing again, that going through all this, but once you actually go through and build the system, you'll understand why it's behaving the way it is and what you need to do in order to account for that. All right, so if it's not close enough, meaning my particle is too far off the surface there, well, then I'm going to have to do something else to it. I am going to need to meet those same initial conditions. The particle is less than the other one. There's overlap. And now I'm going to say, hey, no, it's not close enough. So now I'm going to go ahead and I'm going to actually access the nearest valid surface position. This is geometry point data. Okay, so geom points uses point data, which taps into the geom particles output here, which is point data type. The closest point on the surface comes in. We say, oh, what's that position? That's where we're going to move our particle. Okay, so now our particles should go right onto the surface, just like that. Well, that's all good, except he's too big again, and so there's overlap. So we need to actually modify that a little bit more and reduce his size. So we're going to set it up in an iterative fashion where it's just going to multiply its current size by, say, 0.9. So every frame, it's going to be decreasing until, boom, it stops. It finds a valid place, and it's good to go. Now you can see there's a little bit overlap off that surface. You can modify this and say, oh, just make it 0, and it'll find and stay on that surface. So it has to be 0. It has to be on that, otherwise it just goes over. There's probably a little bit better way to organize some of that logic, but kind of short on time these days. All right, now we're not quite done because there's always a little bit more that we can do. What we're going to find out is that as we add more particles into this system, more packs, let's put, say, 50 packs in there. All right, too many. Well, let's go ahead and, yeah, packs is too many. Let's try 10. Okay, so let's do 10. So you can see as we start to change these down like this, some of these never resolve. They just keep getting smaller and smaller. We've got multiple ones overlapping here on this corner. What we need to do is we need to start to adjust both the big ones and the small ones again. Well, let's go ahead and adjust the big ones. And what we're going to do, it's a little complex, so bear with me. What we're going to do is we're going to detect, is that minimum distance greater than this? Well, we've already determined, is it close enough? But what we're going to do is set up a condition for greater than. And again, I haven't gone through all the different logic variants of this, but actually, did I wire that right? But there's probably ways to optimize this. All right, so let's set up the minimum distance there. This goes into here. And what we're going to do is essentially just duplicate a bunch of this. We're going to end up modifying those source, or I'm sorry, not the source, but the other packs that it found. So even the big ones will end up shrinking down a little bit. Now we need to meet these same conditions. Is the one smaller? Is that negative? Is this on? But now we're going to add another one. So you can see it does get complex. Nice thing about TP is you got a fully visual scripting language. Let's go ahead and grab the size for this guy. Okay, so now you can see that they play a little more nicely together and they kind of jump into place. So that's good. Let's go ahead and save this so we don't have any unfortunate situations. Okay, and now we'll start to increase our amounts here and see if we can see how well the system does. So if we add a Total of 20. Well, you can see that we also get some more issues in here. We do get overlap. So let's actually go do this. I'm going to, oops, the fly is still off. This is where that danger can start to bite you. And we're going to go ahead and say, hey, take my size even and reduce that. Let's see if that helps out. Nope. Forget what it was. I had some solution that made that work, but this one just must not resolve. That's unfortunate. Yeah, not quite there. Alright, well, if we go ahead and modify this one's size anyway, during that first operation, what we find is those pack in better. Let's go ahead and see what happens when we get even more. Yeah, eventually. Well, this one may or may not resolve. Finally. Yep, there it goes. That's awfully small, though. You should build in some sort of detection and kill off if they get too small, probably. But you can see, kind of iterates over, and eventually it'll find a solution. Now, there's probably more elegant ways to do this, measuring the difference in the offset vectors and then setting the size based on that. So we go ahead and hand over this source file to you, have fun with it, and we'll see you around.